Hello class, this is CSE-5250, sections 2 and 60, week 2, spring 2026. I'm the instructor Giovanni Orijuela, and let's begin our look at chapter 1. This chapter is going to be pretty short, and so will chapter 2. I am speed running through chapters 1 and 2 so that we can get to our first API, that is pthreads, all the way in chapter 3. So, again, I am speed running through chapters 1 and 2 just to give you enough context for what we're doing and why. So, one question to consider, or rather several questions to consider, is why do we care about parallel programming in the first place? Can't we just wait for CPU technology to advance? Why build these parallel systems in the first place? And even if we needed a parallel system, can we just write a program that can just make the program parallel for us? Well, these questions over. Pause the video, think about these questions, and then continue watching the video, okay? Okay, let's talk about that now. Okay, so why do we need more performance? Well, for the longest time, and I'm talking like 1980s to 2000s, and probably even before that, earlier than that, up until the 2000s, CPU performance reliably doubled, roughly 18 months. This observation would become known as Moore's Law, made by the first observed by Gordon Moore. It's not a law in the physical sense, but it has been the biggest driver for more power, because performances kept doubling and doubling every 18 months. We basically saw that as progress for CPUs, just becoming more and more powerful. And during this time, if you wanted a more powerful computer, all you had to do was wait for a more powerful computer to hit the market. Here's the thing. Ever since the early 2000s, this trend has ended. Instead of yearly performance gains of like 50%, it was like more like 4%. It's only around 2005 that CPU manufacturers started to produce multi-core CPUs. And core counts only went up from there. It was, for the longest time, 4 cores to be the most common core count for most high-end CPUs, though higher-end CPUs might have had more cores than that. But I still remember a time when I was first building my first computer in the mid-2010s that 4-core CPUs were basically the norm. It was only around 2017 that I first got I bought my first 8-core CPU. This was a Ryzen 7 1700. One of the, probably the first easily, readily available, cheapest 8-core CPU that actually worked too. And ever since that point, AMD has basically more or less dominated the CPU market. There's an interesting story as to why that is, but to appreciate that, you gotta remember that AMD is not a company that can make its own CPUs. Rather, they make the plans for their CPUs, or I guess parts of it, and then they send those plans to the other companies to make the CPUs for them. The two companies in mind are Global Foundries and a second one called Taiwan Semiconductor Manufacturing Company, TSMC. But even that has its own backstory, because the equipment needed to make these CPUs came from an even lesser known company called ASML. There's an entire Veritasium video about this, and also gets into why we couldn't get CPUs any faster. There was yet another reason why we couldn't get CPUs any faster. And that is because it was getting harder and harder to make CPUs any smaller. But again, I am already getting a little bit sidetracked. So I guess if you wanted to add yet another bullet point to this, not only did Moore's Law begin to fail, so did our manufacturing methods. Anyway, my point is, up until the 2000s, CPU performance doubled roughly 18 months. That is exponential. And the problem with exponentials in general is you cannot find a pure exponential in the wild. There's always going to be some point at where growth is going to taper off. Anyway, up until the 2000s, if you wanted a more powerful computer, all you had to do was wait. It's only around CPU performance gains begin to taper off around the 2000s, and to get more performance, CPU manufacturers started to add more cores to their CPUs. Why do we need this much performance? Because a lot of the big computing problems these days just require it. Climate modeling, for example. You need to simulate like trillions of air particles, and that's hard. Protein folding is a very interesting use case because for the longest time, the only way for researchers to know the shape of a protein is to collect enough of it to form a crystal and do crystallography to figure out the shape of the protein. And now there are specialized artificial intelligences that can fold the protein with up to 90% accuracy and even more. And all of this was only possible within the past decade, or rather, the breakthroughs for this only in the past decade. There's yet another Veritasium video about this, which is its own subject. This is an interesting subject that the YouTube channel Veritasium has covered, and it is interesting because we went from a few 100,000 proteins whose shape we have figured out to 200 million. If that's not exponential progress, I don't know what is. That's estimated to be every protein known to exist in nature, by the way. Drug research is another topic. Energy research is another topic. Data analysis. The forms of AI that we would associate with this decade, or rather the latter half of this decade, ChatGPT, Google Gemini, DeepSeek, all of those forms of artificial intelligence, which I would personally class as generative AI because AI is its own field that has existed for decades already. My point is, all of these things require lots of computing power, and a single core CPU ain't gonna cut it anymore. So, what's wrong with CPUs tapering out in the early 2000s? Well, clock speed at one point was the main factor for determining how powerful a CPU is. Though technically it's not the only factor. There are others such as instructions per clock cycle and others, but even if we went by clock speed alone, we can't get it any faster because heat dissipation. The faster you run your CPU, the hotter it becomes, and at some point you can't dissipate that heat fast enough, and the CPU melts down. Of course, it's gonna glitch out long before that, but even then, it's just still gonna cause issues such as causing irreparable damage. Why was this exponential progress possible in the first place? Because the smaller we can make our CPUs, or rather the transistors on the CPUs, the smaller we can get them, the better, because if we can make the transistors on a CPU smaller, we can do the same amount of work for less energy, or do more work for the same amount of energy. In either case, that is more processing speed, well, and that's just more speed. The disadvantage of all this is, as I said, if you increase a CPU's speed, the hotter it's going to get, and at some point, you can't keep the CPU cool enough to have it reliably run for long. And it's not like you can't get a CPU to run that fast for that long. The issue is how costly is it to keep it that cool? Yeah, I have to talk about this one point. I say air cooling has reached its limit. It's not that there aren't other solutions like liquid cooling. It's just that they are prohibitively expensive. Well, air cooling is still the most cost-effective way to keep a CPU, or just your computer in general, cool. But look up the records for highest CPU clock speed. You might find a few figures that are absolutely eye-watering. The record for the longest time was around 8 gigahertz, which was recently beat by another CPU that was running at 9 gigahertz. But the only reason why that was possible was because these people were cooling these CPUs with liquid nitrogen. No, not just liquid nitrogen, liquid helium. I don't know about you, but I do not have a canister of liquid helium in my house. As I said, clock speed was the only metric that was used to indicate that a computer was fast. Not that it was the only metric, but it was the metric that most people thought about. That's no longer the case now. There are other metrics as well. But nowadays, clock speeds, the highest, the top of the line CPUs that you might be able to get these days, top out at least 5 gigahertz now. For the longest time, it was like around 2 to 4 gigahertz. 5 gigahertz at that time was unheard of. And now these overclockers were able to get it to 9 gigahertz. Also, not including server or workstation CPUs, the highest core count available is 16 CPU cores. Though earlier than that, it was 8. But even during that time, it was more common to find 4-core CPUs. It was around the latter half of the 2020s that AMD started to come out with these bonkers powerful CPUs. Of course, we have Ryzen, Threadripper, and then Ryzen 9. The Ryzen 9 CPUs, those are 12 and 16 core CPUs. Not meant for gaming, though you can game on them, but rather meant for users who legitimately needed more computing power. The kind of people who are probably making videos doing data science, rendering 3D models, the kind of stuff that would justify getting a Threadripper if, for example, they had the budget for one. Personally, I'm more familiar with the AMD lineup. I am not familiar with Intel's lineup at all. So, whatever I have to say about CPUs is from an AMD lens because that is the brand that I am most familiar with. Okay, my point is, multi-core CPUs were only like 4 cores at most. Only recently were we able to get to 8 and 16 cores. We also used to use clock speed. We also used to use clock speed as the main metric for computer performance, though it is not the only metric at all. So, with that, why do we need to write parallel programs? Well, most programs that were ever written, and most programs that you will have personally written, chances are, those programs are meant for single core systems, and they can't use more than one core. You could run multiple instances of the same program, but that doesn't really help. If you have 2 of the same program running, those are 2 separate instances. They cannot talk to one another. So, why we need to write parallel programs? Because most programs are written for single core systems, and they cannot use more than one core. There are 2 ways we can to handle this. We can convert existing programs with a special program that can parallelize code, or do it the hard way, write it ourselves. turns out researchers have found little success in writing such converter programs. Even in cases where certain operations can be parallelized, the resulting code may end up being slower, so at worst we have to design our algorithms from the ground up, basically rewriting a program from scratch so that it can utilize multiple CPU cores. It also means that some older programs just won't benefit from multiple CPU cores. And some of those programs may be video games, because video games are just computer programs, because video games are just a type of computer program after all. A lot of old programs just won't be able to use more than one CPU core. The only way that they can is if you can somehow grab a hold of the source code or meticulously decompile the whole program and then rewrite it from the ground up so that it can utilize multiple CPU cores. And as I said, there has not been any luck in writing converter programs, so this is an effort that has to be done by the programmers to write parallel programs. So how do we even do that? So how we write parallel programs depends on how the work is partitioned between multiple cores. And there are two ways to do this. The first one is task parallelism, where different tasks are concurrently executed on different CPU cores, and the other one is data parallelism, where the same task is concurrently executed on different CPU cores. Here's a physical analogy that you may have been familiar with yourself. Imagine you had to wash multiple loads of laundry, and you only had access to one washer and one dryer. How would you do that laundry? Well, simple. Just get the first load started, and once that first load get the first load started in the washing machine. Once that's done, move everything from that washing machine to the dryer, and as that is running, you start the next load of laundry in the washing machine. Once the dryer is done, you put that aside, move everything from the washing machine into the dryer, start another load in the washing machine, and while the third load is washing, the second load is drying, you start folding the first load. By the way, that is called pipelining. Yeah, that is called pipelining. The solution here would only ever make sense if your has a circuit breaker cannot handle the washing machine and dryer running at the same time. Wash one load, dry, fold, and then repeat with the next load. This is not only slow, but also inefficient. And the only reason you would ever do this is, as I said, if you somehow cannot run your washing machine and dryer at the same time. So, the pipelining solution is going to be faster because now you have different loads at different steps of being processed happening at the same time. You're able to get more stuff done at once. So this is a 3-step pipeline. There's another example of pipelining. If you've ever been to one of those automated car washes where you just drive your car onto a conveyor belt and it just drags your car through different stations, that is yet another example of pipelining. The prototypical example to explain what pipelining is like an assembly line. I personally like the car wash example more because it's probably an example that you might just be a little bit more familiar with than you would be with an assembly line. But the concept is still the same. You have different stations at which your cars can be at in the assembly process if we're talking about an assembly line, or the car wash process if we're talking about a car wash. If a car needs to skip a station, it just goes through that station without any work being done on it. If we were talking about a car wash, let's say there are 3 different stations at a car wash. Actually, no, 5. Wash, wash, soap, rinse, wax, and tire shine. Say a driver wanted the most basic wash and did not pay for tire shine. Once that car reaches the tire shine station, it just goes through this tire shine without any tire shine being applied. There are still some issues with pipelining, such as what if a car gets stuck? I know this because I have made a car wash break in that fashion, which I'm sure was fun for everyone else ahead of me. But anyway, that is a situation like that is called a stall because the whole thing just stalled. It's something that you don't want in a pipeline, but this is probably something that you will have learned, or at least have touched on if you have taken CSE-4010, that is computer architecture, which is likely going to be the case. Here's another solution for the laundry example. If you have too much laundry that you have to wash, give up and go to a laundromat. So this is closer to parallelism as we're going to be seeing in the course. Because at a laundromat, you have access to multiple washing machines and multiple dryers. Just divide your laundry into however many loads you need to, and just shove them into however many laundry machines you can get away with. Once all of those are done, you divide it again into however many dryers you can get away with. Though even this is not a perfect analogy because from my experience, laundromats have different sizes of machines. Like you have your small machines that are meant for general laundry, and then you have larger machines meant for bed sheets. Also, these machines will run for differing amount of times depending on the settings and of course depending on the machine as well. There's also drying times that may also be variable because different types of laundry have their own drying requirements. Some things just dry faster than others. There's also a load balancing issue because you have to divide everything evenly across all of your laundry machines. Oh yeah, and of course there's the work of just dividing it all up and getting everything back together. Oh, and at the end of the day, you still have to be the one who has to fold everything. Unless you have some helpers with you. The textbook has a different example. Say a professor is teaching a 100-student class and has 4 TAs helping her out. The professor gives out a test that has 5 questions on it. How does the professor and her 4 TAs grade all 100 tests? Well, there are 2 solutions. Solution 1 is based on task parallelism. The TAs and the professor each grade a separate question. In total, each person will have graded 100 questions each, but again, each one will have graded a different question. That's task parallelism. So, the TA grades questions 1, 2, 3, and 4, and the professor grades question 5. That's task parallelism. So you have given each person a different task to do. Solution 2 is data parallelism. You divide the work. This is 20, so that each person grades 20 tests each. It's the same number of questions being graded, but each will have graded all the same questions. This is data parallelism because everyone's doing all the same work. It's just that they're doing it on different tests. They're all grading the same 5 questions. Though there are a few things to consider with this example as well. Communication. In solution 1, each test will have to be sent to 5 different graders. So basically, if you can imagine yet another assembly line, say all 5 graders are just grading things all on one table. Grader 1 grades question 1 and then passes it off to grader number 2 who grades question 2, and so on and so forth. That is a communication issue that you have to resolve in solution 1. Okay, that's pretty simple. But what if, because the professor is going to be more knowledgeable about the material, she may end up grading tests a little bit faster than her own TAs. That is a synchronization issue. if we assume that all 5 graders can grade at the same speed, you gotta give everyone the same amount of work, which might not always be the case. What if in solution 2, one grader finishes first even with load balancing? And what if in solution 1, one grader is faster at grading a specific question? I don't know if you've ever played the telephone game. Or, not the telephone game. It's a game called the fax machine game, where you draw a sketch and then you give it to someone else. That someone else has to write a verbal description of what the picture is and then pass off that verbal description to someone else, who then has to recreate the original drawing based on that description. You might know this game as Gartic Phone. That's the computerized online version that is basically the same game, just wrapped up in a means where you don't need to have everyone physically present to play the game. So that's a synchronization issue that Gartic Phone resolves by putting everyone on the same timer. But when I played the fax machine game as a high school student, there was the issue of, okay, someone has to catch up. And that's the synchronization issue that I am trying to demonstrate in here. What if someone grades slightly faster than others? Okay, so finally we're going to be looking at what we're going to be doing over the course of the several weeks we have for the class. Basically, we're going to be writing parallel programs using 3 different APIs. I would like it to be 4, but I'm not sure if everyone has access to an NVIDIA GPU. So it's going to be 3. OpenMP, pthreads, and MPI. Though I'm actually going to start with pthreads first, and then MPI, and then OpenMP, and then MPI. So we can classify these APIs in 2 ways. How do they share memory, and how many independent data streams the CPU cores can handle? So the first thing is shared memory versus distributed memory. In a shared memory system, multiple CPU cores all access the same memory. If a CPU core updates something at a memory location, all other CPU cores after that can easily access that updated value. That is shared memory. Distributed memory is where each CPU core has its own memory separate from that of all the other CPU cores. If there is an updated value, that CPU must send a message to all other CPU cores, usually over a network. So shared memory and distributed memory. So regarding instruction streams, the CPU cores can either have their own control units so they can operate independently of one another, or they all share a single control unit so they're performing all the same instructions just on different data. What do I mean by share a single control unit so they perform the same instructions on different data? Well, go back to the example of the TA and the professor. Data parallelism is where the graders are all grading the same 5 questions each. That is basically them sharing share a single control unit. Since there are 2 ways to classify memory setups and 2 ways to classify instruction stream setups, there are therefore 4 different types of programs organized in a chart that looks like this. This is called Flynn's taxonomy, and it's been updated over the years, but the base version is you have 4, maybe 5, maybe 6 different types of programs. So single instruction, single data, 1 instruction stream, 1 data stream, basically your standard sequential programs. For our purposes, that is boring. Chances are, all the programming you will have ever done has been single instruction, single data. For our purposes, this is boring. We want to do the parallel stuff, actually. The next one after that is single instruction multiple data, and that is parallel. That is data parallelism. One instruction stream working on multiple pieces of data at once. Multiple instruction single data is multiple programs working on the same data. And finally, the most general of them all, multiple instruction, multiple data, different instruction streams working with different data each. There is a fifth category that is shown here, and that is single program multiple data. Copies of a single program allowed to execute different parts of its code on different data. If you go to Wikipedia, you'll find hints of a sixth category, but we don't have to get that far right now. But what we're going to be doing is exploring most of this taxonomy by writing different parallel programs using different APIs. A few notes. Not all authors agree on what's meant by concurrent, parallel, and distributed computing. Different textbooks might have differing definitions, but most authors will try to make the following distinctions. In concurrent computing, a program is one in which multiple tasks can be in progress at a time. In parallel programming, a program is one in which multiple tasks cooperate closely to solve a problem. In distributed computing, a program may need to cooperate with other programs to solve a problem. You may have heard concurrent computing before, or multitasking. Even in the early days of computing, when all we had were single-core CPUs, it was still possible to fake the appearance of a computer working on multiple things at a time by having it switch between different tasks really fast. That's concurrent computing, though you might have heard it under the name of multitasking. Even though such a system can work on one task at a time, there are still multiple tasks in progress. Or I guess that should be the other way around, but still. Even with a single CPU core, you can still fake the appearance of a single core computer working on multiple different things at a time. Additionally, there isn't a clear distinction between distributed and parallel computing, though with parallel computing, the cores tend to be physically close to one another, and with distributed systems, they tend to be more loosely coupled, and the computers are allowed to be physically distributed over a large area. And another word of warning, it might be tempting to write parallel programs by the seat of your pants, but that's going to be a big mistake. Every parallel program contains at least one serial program. Serial meaning non-parallelized. Since we almost always need to coordinate the actions of multiple cores, writing a parallel program is going to be far more complex than writing a serial program that solves the same problem. We're gonna get to those potential hiccups when we get to pthreads, by the way. And OpenMP is no different either. There are some hiccups that we might encounter that we're going to have to resolve simply because of the nature of parallel programming. Ever heard of a race condition? Well, that only exists because race conditions only exist when there are multiple CPU cores competing for something. Competing for what? Competing for access to a resource. This is also something you might have likely learned from operating systems, but it's going to come up again in parallel programming. There's a song where, in the bridge, this guy gets a tattoo of the number 13, but the tattoo parlor screws it up by writing the number 31 instead. I like to think that screw up was because of a race condition. Anyway, that's going to be it for Chapter 1, and stay tuned for Chapter 2, and finally Chapter 3. Chapter 3 is where we're going to write a Hello World program, and then we're actually going to be starting our discussion on how to write a parallel program. Specifically, we're going to write a multi-threaded program. pthreads is going to be a little bit tricky because the POSIX thread library is something that is unique to Unix systems, so Mac and Linux systems, you can just write a program and you can just access that API without any issue. If you are on a Windows system, I recommend getting a hold of a Mac if you can, or downloading VirtualBox and installing Yeah, downloading and installing VirtualBox and setting up a Linux virtual machine. I have instructions on that on Canvas. You can refer to that, but get that done as soon as possible so you can actually start working with pthreads. Okay? Okay. All right, that's gonna be it for this first video. Okay, chapter 2. I'm gonna be adding this part in addition to the part on chapter 1, just so I can have it be ready as one big video. So chapter 2 is gonna be a review on the von Neumann architecture, but it's also gonna be a discussion on Amdahl's law, which we're gonna get into in a little bit. So likely you will have learned about this architecture probably as early as CSE 4010, maybe even a little sooner than that. But the von Neumann architecture is the main architecture that is used in virtually all computers today. This is an architecture that consists of main memory, a CPU, and some bus that connects the two together. The CPU itself can be divided into a control unit, which is responsible for deciding which instructions to execute, and a data path that is responsible for executing those instructions. In the CPU are little pieces of memory called registers. They only hold one word each. You have registers that can store working values, but you also have other registers, such as one that keeps track of which instruction are we at right now. How fast data can move between the CPU and the memory depends on how fast that interconnect is, and that separation is called the von Neumann architecture. No, that separation within the von Neumann architecture is called the von Neumann bottleneck. I misspoke there. Computer scientists and computer engineers have experimented with modifying this architecture, and the one modification that you will likely have heard about is called cache. So if we have registers at the highest level of memory, because in operating systems you will have likely learned about the hierarchy of memory. At the very top we have registers, below that we have main memory, and then below that we have secondary storage, which is usually going to be hard drives. Of course it's going to be a lot finer than that, because computers these days have options for what constitutes secondary storage. You might also have, in addition to, or possibly replacing hard disk drives, you might also have solid state drives. So you actually have two options for secondary storage. You also have removable media, such as flash drives, CDs, DVDs, and Blu-ray discs. But you also have another tier of memory below that. That is archival media, for which flash drives might also be there because it's removable. What also counts as archival media is tape drives. Those are super slow, but they're perfect for storing backups. Okay, so now we have this memory hierarchy. We have archival media at the bottom, secondary storage above that, which includes hard disk drives and solid state drives, main memory on top of that, and then registers at the absolute top. So cache is a form of memory that lies between memory and the registers. When the CPU executes an instruction, well, first it has to get that instruction from memory. But the thing is, the CPU typically operates far faster than main memory. So it's going to take several clock cycles for the CPU to even get an instruction from memory. All the while, the CPU is sitting there doing nothing. And that's actually the last thing we want to do. We want to keep the CPU busy. So, if it's the very first time the CPU is accessing memory to get an instruction, of course nothing's going to happen for that first little bit. But say that CPU is accessing an instruction at address 100. Chances are it's going to have to access the memory address after that. So at address 101, 102, 103, 104. So when the CPU accesses that address for the first time, we're gonna make a copy of that and everything next to it and store it in cache. That way, when the CPU needs to access that address again, it doesn't have to go to memory and wait however many clock cycles to get the next instruction. It just goes to the cache, which is already loaded. It's already preloaded, so it has to wait less time to figure out what to do next. The reason why we copy that address and everything else next to it, because there's a good chance that if we need something at this address, we're going to need everything around it as well. That is called the principle of locality. CPUs these days generally have 3 levels of cache, so level 1, level 2, and level 3 cache. If the CPU needs to access something, it first goes to the level 1 cache. If it finds what it's looking for, that's a cache hit. We don't have to go any further than that. If it doesn't find what it's looking for, it's a cache miss, so it goes to the next level of cache. If it still doesn't find what it's looking for, it goes to the next level of cache after that. And if it's at level 3 cache and it still hasn't found what it's looking for, then it's going to have to go all the way back to memory. But once it's found in memory, the system will just cache everything into the appropriate levels of cache, so the CPU will simply just go to the cache after that. Here's another modification to the von Neumann architecture: multiple issue. Such processors replicate functional units and try to simultaneously execute different instructions in a program. So say we have a vector of values, and actually you have 2 vectors of values, and we have to perform a vector addition operation. So say we have 2 1,000 element vectors, x and y, and we want to calculate z. To calculate any one value in vector z, we have to add the corresponding x and y values. So zi equals xi plus yi. We could just have a single control unit calculate z0 and then z1 and then z2 and then z3. Instead, what if we just had 2 adders running at once, so that one adder does z0, z2, z4, z6, and so on, and the other adder does z1, z3, z5, and so on. If we can do that, then we just cut our execution time for this operation in half. The key to this is to figure out what instructions we can execute simultaneously. But another option is have the system make a guess. This is called speculation. This is where the compiler or the processor makes a guess about what instruction to execute next. So say we have this block of code, z equals x plus y. If z is greater than 0, we do this instruction. Otherwise, we do some other instruction. So say the system predicts that the outcome of z equals x plus y will be positive, so then it executes this code here. However, it's possible that the system will get it wrong. It does this when it's supposed to do this, so the system must be able to backtrack and start over at that point, which is going to waste time because we did all this work for nothing. Now we have to go back and then start over. But this is the risk you take when you do speculation. Instruction level parallelism may be hard to exploit, especially in situations where there is a long sequence of dependent statements. What I mean by that is, consider the example of calculating Fibonacci numbers. So the Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13, and so on, where the next Fibonacci number in the sequence is the sum of the 2 numbers before it. Now, there are ways to calculate the Fibonacci numbers without having to calculate the numbers before it, but if you coded it like this, you cannot calculate the nth Fibonacci number without first calculating the n-1 Fibonacci numbers before that. In this case, you cannot skip ahead. You cannot skip ahead because you don't know you do not know what you're calculating. If you have a Fibonacci number program coded in this way, you cannot skip ahead. Thread-level parallelism attempts to provide parallelism through the simultaneous execution of threads. This can be coarse-grained, simultaneous execution of different threads, or fine-grained, that's simultaneous execution of individual instructions. Simultaneous multithreading, that is a variation of fine-grained multithreading. This exploits superscalar processes by allowing multiple threads to make use of multiple functional units. And it's branded as hyperthreading on Intel CPUs. It's how a 8-core CPU has 16 threads. Or on a Windows system, it's reported as logical processors. I've shown this in the section for Chapter 1, but this is Flynn's taxonomy. We can also use this to organize parallel hardware. For our purposes, we're actually gonna be looking at multiple systems that handle multiple data streams, so SIMD and MIMD. So SIMD systems are parallel systems. Here, an instruction is broadcast from the control unit to the individual data paths, and then each data path either applies the instruction to the current data or is idle. I don't know if you've ever had this situation before in, say, high school or possibly just grade school in general, but sometimes the teacher won't grade the exams, but rather randomizes it so everyone grades someone else's exam. In that case, the teacher is like the control unit. The teacher announces the answer to question 1 is 42. And a student who is grading someone else's exam will do one of two things. Mark that answer as incorrect, or do nothing because it is correct. The teacher then announces the next thing, which is the answer to question 2 is 36. And again, the students either mark it as incorrect or they do nothing. And this continues for each instruction. The end result is the teacher did not have to do as much work to grade all the exams, and to an extent, everyone knows how well everyone did. But this is an example of an SIMD system where you have an instruction being broadcast to all the individual data paths, and then those data paths either does a calculation or does nothing. Suppose you have vector addition. So here's an example from the textbook. If we have n data paths, we can load xi and yi into the ith data path and then have it add the two values and then store it in x. So it's like that example of vector addition where instead of having one data path do one addition at a time, we have multiple data paths each doing an addition at a time, but since there are multiple data paths, we're doing more additions at once. It's also like that teacher who has students grade each other's exams. Also, the fact that some data paths can be idle can pose an issue. If we require in here that yi is positive, then there may be some data paths that are idle while others carry out a calculation. So again, the answer to question 1 is 42. Some students will have gotten it right, some students will have gotten it wrong. One student in particular might have to do nothing because whoever did answer this question got it right, they don't do anything. So that is one thing that can happen with an SIMD system. Some of the data paths are doing something, others are idle. In an SIMD system, the data paths must operate synchronously. In that example of the teacher who has students grading each other's exams, none of the students can proceed to grading the next question until the teacher broadcasts the answer to that next question. Each data path must wait for the next instruction to be broadcast before proceeding. Also, data paths don't have a storage for an instruction, so a data path can't delay execution by storing it for later. SIMD systems are ideal for parallelizing for loops. That's data parallelism. So this example of a teacher who has students grade each other's exams is yet another example of data parallelism. And it also shows some of the what it takes to get such a system to work. Yeah, the teacher will at the end will have graded everything, but the teacher herself did not have to do all the work. That work was instead divided among all of these data paths, basically the students grading each other's exams. So here's like tangent to a GPU. Whoops. So GPUs are, you're probably familiar with what a GPU is, but it's a graphics processing unit that, so graphics APIs use special functions to internally represent the surface of an object, and then they use a processing pipeline to convert that internal representation into pixels that can be displayed on a screen. So we have data that represents a triangle, we have it go through this pipeline, so we can then display a triangle on the screen. Processing a single image requires large amounts of data. On the order of megabytes is probably not uncommon. GPUs therefore need to maintain high rates of data movement. So to avoid such stalls, GPUs rely on hardware multithreading. Though, keep in mind that GPUs are not pure SIMD. They can also be a mix of that and MIMD. Current generation GPUs can run more than one instruction stream on a single core. GPUs have dozens of cores, and each core can execute an independent instruction stream. GPUs can either use shared memory, distributed memory, or for the largest systems, both. MIMD systems support multiple simultaneous instruction streams operating on multiple data streams. Each processor operates at its own pace, so they're asynchronous, and in many MIMD systems, there is no global clock. Unless the programmer imposes some synchronization, at any given point in time, MIMD processors may be executing different statements. So I guess one way to do that is, instead of that teacher having students grade each other's exams, it was that and each other's previous homework assignment. The teacher might also give out the answer keys to the two assignments, and it's up to everyone to keep up at their own pace to grade each other's assignments. Of course, that might open up a whole can of worms of, okay, now it's possible that those answers might be leaked, so the two answers might just be flat out given away unless the teacher changes the answers every time. But that's the gist of an MIMD system if I am to continue with this teacher has students grading each other's exams analogy. MIMD systems are either shared memory or distributed memory. As I've talked about in Chapter 1, shared memory systems, all the CPUs share the same memory. For distributed memory systems, each CPU has its own memory. In shared memory, if a CPU updates a value at an address, all other CPUs can easily access that shared value. In a distributed memory system, if a CPU updates a value, it's going to have to send a message to all the other CPUs saying, hey, this value got updated. In parallel hardware, for parallel hardware, we have plenty of machines and devices that have multiple processors. You might even have such a machine already. You might have a multi-core CPU. You might also even have a discrete GPU. In terms of software, it's a lot complicated. There are programs out there that can leverage multiple CPU cores, Microsoft Excel, Adobe Photoshop, Google Chrome, Blender. Some video games can also use multiple cores now. But still exists the problem that there are plenty of single-threaded programs out there. We can't get any more performance increases through hardware alone, so we have to turn to programming for those increases. We're going to be looking at SPMD, Single Program Multiple Data. A single executable behaves as though it were multiple programs. If I am thread 0, I'm going to do this set of instructions. if I am some other thread, I'm going to do this other set of instructions. We're going to be doing this using an if statement. A thread with a specific ID will do some task, otherwise it'll just do some other task. And sometimes it is trivial to get parallel performance. This add operation, for example, can be parallelized by dividing the work as evenly possible. So, this is yet another example of a vector addition where we take one vector and then add to it another vector. But we're storing the result in the first vector. So if we have 1,000 elements and 4 threads, we can divide the work so that each thread calculates 250 elements each. So say one thread adds the first 250 elements, the next thread calculates the 250 elements after that, the next thread calculates the next 250 elements after that, and so on. This is said to be embarrassingly parallel. Like, super easy to parallelize. The steps for doing this is as shown. Divide the work so that each thread gets roughly the same amount of work, that's load balancing, and the amount of communication between each other is minimized. Arrange for the threads to be synchronized, and then arrange for communication among those threads, though the last two steps are often interrelated. A few dangers to consider, and again, this gets back to operating systems. If multiple threads or processes attempt to simultaneously access the same shared resource, you have the danger of introducing a race condition, or in some cases it's called a race hazard. In some cases, we need to make it so that a process or thread only one process or thread can access that thing at a time. That's called mutual exclusion. As a programmer, if there is the danger of a race condition, it is on us as the programmers to enforce mutual exclusion. And finally, we get to Amdahl's law. So, this is a formula that calculates the potential speedup for a program given parallel and non-parallel parts of the program and a CPU with some number of cores. Maximum speedup is based on the number of cores available and the proportion of the program that must be performed serially. In this formula, S is the proportion of the program that cannot be made parallel. 1 minus S is the proportion of the program that can be made parallel. X is the number of CPU cores the program can use, and Y is the speedup. So here is a geometric intuition for Amdahl's law. So say we have a program that can be parallelized. It will always have two parts. The portion of the program that can run serial code, that's on the left here, and the portion of the program code that can run in parallel, that's the green code on the right. With one CPU core, the program runs for 100% of its runtime. The single core executes the serial portion and the parallel portion. Not necessarily in that order, but it's gonna have to run both the serial portion and the parallel portion. With two CPU cores, the parallel section's work is divided now between two cores. Okay, so one CPU might have to do the work of the serial portion, but once it enters the parallel portion, that work is divided between it and the other core. But the overall effect of having the work but divided between the two is that this parallel section is done in half the time because we have two CPU cores doing half the work together. With 4 CPU cores, now that parallel section, we only have to be there for 1/4 of the time. And the more cores we add, the smaller and smaller time it takes to even be in that parallel section. So in this example, we had half the program running in parallel and then half the program serial. By adding more cores, the program was approaching a runtime that was half the original runtime when running on one core. So it means the maximum theoretical speedup, if we push the number of cores to infinity, is a 2x speedup. This only gets better if the proportion of parallel code is large compared to the serial portion. In that case, we can throw more cores. Though, if you were to graph Amdahl's law, it's going to be an S-curve where you're gonna get huge and huge speed ups, and then it's gonna plateau, and you're barely gonna get any more speed up. Inversely, if nearly all of a program's code is serial, you're not gonna get any speed up, if at all. It will barely run any faster. So this is just a geometric intuition for Amdahl's law. I wanted to show this in a visual way because, of course, I feel like it's a little more intuitive to think about Amdahl's law as these blocks where you just cut one block in half and then cut each half in half and then line them up so that the overall time spent in the parallel section is going to be smaller and smaller and smaller. So yeah, that is Amdahl's law. Later this week, I am gonna get you started with your first programming assignment. It's just gonna be a Hello World program using pthreads. So with that, I think that's gonna conclude our discussion on chapters 1 and 2. And please get your computer system up and running so that you can start working with pthreads as soon as possible, because later this week I am gonna start talking about pthreads. Okay? Alright, that's gonna be it for this video. It's gonna be a little awkward because I had to splice this video at the end of the part for chapter 1. But yeah, that's gonna be it. We're gonna be looking at chapter 3 next. Okay? Alright. See you next video.